Black holes are one of the greatest scientific enigmas in our universes. Theorized in 1915 by Einstein and 1783 by John Mitchell, these celestial bodies were believed to have such strong gravitational attraction that even light was not able to escape. These cosmic bodies were made up of several unique phenomena that gave such powerful forces to black holes. First, let's look to the outer edges of the black hole, where relativistic jets and accretion disks surround the celestial body. A ring of gas and dust orbits the black hole at unprecedented speeds, with some even passing through the event horizon, a point where no matter or light can escape, thus feeding into the black hole. This is considered the point of no return. In turn, the black hole produces jets of radiation at almost nearly the speed of light. These gases that travel through the event horizon eventually reach the singularity right here, the center of the black hole that collapses matter with near infinite density. Near the event horizon, a bright orange ring right around here surrounds the black hole because of an emission of photons due to nearby jets and the accretion disk. This emission is dubbed as the photon sphere, as the singularity distorts the motion of these photons into a relatively circular manner. This is how we can see that bright orange color.
But how do other objects actually revolve and behave around black holes? Major astronomer and physicist Carl Schwarzschild considered this notion, developing the Schwarzschild geodesics equations, a set of differential equations that model the motion of objects and light rays around a non-rotating black hole. Specifically, we must look at this differential equation right here. So this can look really intimidating at first, so we should start by breaking it down. Starting with r is the radial distance between the object in orbit and the center of the black hole. When the object moves, r changes. T here is time, more specifically the proper time experienced in the object's path through space. As the object moves through the curved space around the black hole, we are using t as a sort of stopwatch to track time. Therefore, dr over dt is the rate of change of r with respect to time, or the radial velocity. It represents how fast the object is moving relative to the black hole. This helps us understand how the radial distance r changes over time. The term 1/2 times dr over dt squared as a whole represents the kinetic energy, which is something to actually keep in mind for a little bit later. Moving on to our next term, V of r is the effective potential. Rather than adding each individual force onto the object separately, the effective potential packages them all together into a single function. It covers the pull of gravity inwards and the outward impact from the angular momentum, which is the object's tendency to move away from the center because of its rotation. And the effective potential formula itself can be written as negative m over r plus l squared over 2r squared minus m l squared over r cubed. And this actually comes from the Schwarzschild metric, so that's also an interesting thing to take note of. Finally, we have epsilon, and this is the total energy of the object per unit of mass, and it is a conserved amount. Now, when we observe this equation with all of our new knowledge, we can actually notice that the differential equation is structured like a conservation of energy equation, where the kinetic energy in the first term plus the potential energy in the second term is equal to the total energy in the final term.
But finally then, how can we see this differential equation manifest within tangible applications of physics in real life within the first place? And why is it so important? With this differential equation, we are able to analyze and predict the curvature and behavior of objects or rays orbiting around black holes. With this, we, along other scholars of physics, can optimize pre-existing scientific principles like relativity and gravity to further understand their influence in space, especially regarding black holes. By better explaining these notions, we can apply our knowledge towards other orbiting bodies such as planets like Mercury, a body whose orbit didn't follow scientific predictions at the time. Today, we have used this differential equation to model orbits best through the Global Positioning System, or as we often dub as GPS. The Schwarzschild geodesic effectively makes use of Earth's relativity to thus utilize Earth's gravitational field to accurately approximate location accuracy. This is especially vital in preventing potential errors in navigation. Additionally, these geodesics can better explain how extremely strong forces of gravity can affect surrounding objects, given their position relative to the black hole. This looks like asking whether light can escape at a given point, or how much slower or faster an object is, depending on its position relative to the black hole. These analytics are especially important on humanity's journey to learning the ongoing mystery of black holes further, as these celestial bodies are still under great discovery and potential scrutiny. Look to the first black hole image that humanity could capture in the Event Horizon Telescope collaboration. Scientists at the time had to utilize the geodesic equation to better visualize how light behaved around the black hole to get the clearest image possible. With that being said, these discoveries can help us broaden our understanding of relationships of black holes, and maybe someday we ourselves, how we can make use of them. While we could use them to benefit us, we would hope to prevent any poor goon from being sucked into the trenches, while we would also wonder, how far can humanity go without passing no point return? Thank you.